Okay, let's get started. We had a switch where we're dealing with the geometry problems this week. So we're in chapter 13 this week. We'll go back to chapter 12 next week. But question for, first of all, is let's go through the geometry problems. How many people have done all 4 of them? Nobody. How many people have done 3 of them? Nobody. How many have done 2 of them? Nobody. How many have done 1 of them? Okay, good. Okay, and how many have done none of them? Okay. So the good news is that bad news is people got fewer problems. The good news is it means people have to think for themselves today, and this is something that's good because let's take a look at the problems of the day. Of the ones that you've gotten, which ones did you get? Dog and gopher. Dog and gopher. And what about you? Okay. So let's talk about this one again. Okay, who wants to talk to me about dog and gopher? Tell me what dog and gopher is about. Okay, right. So again, so we have a bunch of points in the plane. We have a dog position, and we have a gopher position. And the question here is that the gopher would want to run, the gopher wants to run away from the dog. The gopher can run, the dog runs twice as fast as the gopher. That, I guess, is the problem, right? And the question is there a hole that the gopher can get to before the dog will get there? Okay? So what is the problem? Any questions about what this problem is? Okay? Is this problem finding the closest hole to the gopher? Okay, that's, I guess, the first question. The answer is no, right? Why not?
The hole is far away from the gopher, and also far away from the dog.
Right, so there's a difference here because I guess if you have a line where you've got dog, gopher, hole, it might very well be the case that that although this hole is further away, okay, because it's longer for the dog as well, right? So what did you do here to solve this one?
Just calculate for the distance from the gopher and the dog.
The distance from every hole for the gopher and the dog, and found whether or not there's one that's twice as long as the other. Okay. Anything else? Any other solution there? So what is the time complexity of that? Of finding the closest point for the, that's going to be basically linear in the number of holes. Is that right? Okay, there's as much you can do about that here, in general. Okay? Any questions? How do we get the combinational geometry? There is a related problem, just so we have something to talk about. In general, what would you do for the following kind of a problem? That's linear. We saw that it's linear time to find, even if it was the closest, find the closest hole to the gopher. In linear time, we could find the closest hole to a gopher, right? And if we're only going to do that once, there's no real faster way to do it. But in general, suppose, let's say we had a problem where we had large numbers, let's say we had points that we were looking at, and the points weren't going to change. But every once in a while we introduce a new gopher, and we say, where is the closest hole for that gopher? And then, where is the closest hole for this gopher? Is there anything better that can be done in a world where you have a fixed set of points and you want to find the nearest neighbor to a new one than repeatedly linearly scanning through all the gophers?
Sum the holes by x-axis and y-axis.
What?
The sum the holes by x-axis and y-axis.
So one idea might be saying you sort the holes according to x and y-axis, right? So if you sort them by the x-axis, it's going to look like this. And the y-axis, I guess the y-axis, I guess, right? X-axis is this. What about it? let's say, what you're trying to say somehow here is that this should be useful to helping me find what the closest point is if I knew what bucket it's in, right? That's sort of what you're trying to idea is to decompose the world into these kind of slabs. And I don't immediately see how those slabs are necessarily helpful to you. Okay? People see that one? Okay? Because I guess the defining lines for these slabs could be the points here, 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 and here, right? Which could all be very far away. So it's not obvious that this data structure will help you very much, right? Anybody come up with another data structure that might help you more? Okay? Just to sort of, you know, maybe getting a little bit beyond, out of the scope here, but let's just think about that. What would be a good data structure to help you do it? Okay? One idea, okay, so when you get into computational geometry, we may talk about Voronoi diagrams. Has anyone ever heard of a Voronoi diagram? Well, one fancy structure would be to build the regions around each point, which are closest to that point. I'm now trying to do this in a way, and maybe I'll get this right, or close to right. So one possibility would be to build, actually I'm not, let's say I'm going to try to build it this way. It's not quite the right structure. Would be to build a decomposition of space. Well, like that. Build a decomposition of space into regions, such that all the points within a region have as its closest point the same thing. Does everybody see that? So one way to do it is to build this structure and then search that structure. And that, when you talk about computational geometry, might be a method for that. As a more practical method, I guess, there's ways using things that would be other decompositions of the points. One possibility would be to decompose the, let's say, the points into 4 quadrants. And then now ask myself, if I'm looking for the nearest neighbor to this, I find the nearest neighbor within this quadrant. And if the nearest neighbor within this quadrant is far from the boundary, is close, relative to the distance from me to the boundary, my nearest neighbor in this quadrant is nearest neighbor overall. Does that make sense? And so you can imagine decomposing the region into a hierarchy of boxes, okay, in such a way that as you go through this tree of boxes, okay, you find out what is the nearest neighbor within the appropriate box that contains you. And then you'll know something about what other boxes might contain the nearest neighbor. And by searching through those, that's a more practical way of doing it. Does that make sense? I mean, we'll sort of see that. For the purpose of the programming contest, it means nothing to you, okay? But for the purposes of understanding, there are these geometric algorithms for some of these things, and data structures. That's probably good education. Any questions? Any other questions about data structures for nearest neighbors and things like that? Okay?
I want to know the time complexity of the second solution.
Okay, so the time complexity of the second solution.
Is it called 2D Salzman tree?
Okay, so there's several different hierarchical structures like that. Okay, so you didn't ask it, but just to show off. If you do this right, in this one, you would be able to answer it in log n time in the worst case. Okay? This kind of a structure is something called a KD tree or a quad tree. There's different variants that we're talking about. But the basic idea here is that we are decomposing. Let's say we're going to divide the space in half each time. That would be a 2D tree, right? Maybe we find first a point, the line that decomposes the x-axis equally, right? Then we go according to the y-axis, find on each side where is the point that splits the points in half, right? And then we do this recursively. On this side up here, we would decompose it up here. On this point down here, maybe we decompose it at a fourth point just to make it comfortable. There. Okay? Here. There. And in principle, since we split the number of points at each time, the height of the tree should be logarithmic. Do you agree with that? Okay? So it will take logarithmic time to get to the right box containing it. The harder question is then, what other boxes do you want to have to check? Right? Once you have found, let's say you're looking for this query point. I want the nearest neighbor to this. In logarithmic time, you'd be able to figure out which cell it is in, your point, right? You go through these constant number of points and say, this is closest to my target point. But we have no, it could very well be because the point that we're querying is very close to the boundary. Maybe it's also in this. And the real question is ultimately going to come down to, it's more a heuristic thing with this kind of data. I can't give you an absolute worst case thing. But I can tell you that if you do a good decomposition, you shouldn't have to check many boxes. And it should be log-ish. That's how I would talk about this. There are more precise guarantees depending upon how you do the KD tree and some other things you build. But that's the way to think about it. Okay? Does that answer your question, more or less?
Yes.
Okay. Question?
The first one is log n.
Well, the first one is not obvious, perhaps, that it's log n. It requires some fancy computational geometry to know how to do this. Okay? So it involves, actually, to be precise how it would involve. First, you have to build the Voronoi diagram. Then the way you would do it is actually, you would construct a triangulation of this thing. Okay? And now then the problem reduces to what triangle contains my point, right? And there are ways of building a search index on this triangle arrangement to do that search. This is well beyond the scope of what you do in a programming class. But it's why there are people who study computational geometry and why you've got professors like Dolan and Arya on the faculty here, if they study this kind of thing. Professor Mount who's with it. Okay? Any questions? Okay, we'll talk maybe a little bit more about that in computational geometry, but I just wanted to go through this because it's an interesting point. Any questions? Okay, what is the second problem? I don't think there's anything too deep here that we need to now talk about. What is the second problem? Rope rises and rope land. Has anybody looked at this problem? Has anybody looked at this problem? Okay? Tell me about this problem. So the problem is, as we said, you've got a world where you've got a post, a thick circular post. You've got a wire, 2 points, and you want to string a rope between those 2 points. Does everybody see that? If under some circumstances, as we show here, we go scroll down a little bit further, the rope, the shortest distance between them misses the circle. Otherwise, the shortest distance between it is going to go somewhere along the surface of the circle for part of the time. Does everybody see that? The question now is, given these 2 points and the circle radius, the circle center and radius, what is the length of the rope? Does everybody see that? Shortest rope. Any ideas how we can do this?
First check the line X.
Okay, so you're saying the first question is, see if it's this case. You're saying, if you know that it's not going to intersect the post, you know how to do it, right?
Yes.
I know how to do it if it doesn't hit the post. How do you tell now, given a pair of points, how do you tell whether or not it's going to intersect my circle?
There are 2 conditions. The first condition is that the center is far from the line.
So one condition you're saying is that the center is too far from the line. Does everybody see that? That this, I guess what you're saying is this line segment is really part of a line, right? And one question would be that the center is too far from the line. Does everybody see that? How do you find out if the circle is too far from the line?
I use vector computation.
What?
I use vector computation.
Vector computation, what does that mean?
Of course, you give me those points. I can get those vectors. I use vector point with the angle of this.
Okay, you may use whatever you want to talk.
So I have this vector. So
Wait, what vector is this? This is the vector from the center, defined by the center and that point, okay?
So I have those two vectors. I can next here. This one I can compute. So I know this distance. This distance is here is correct. So
Okay.
So I can get cosine theta and sine theta. So I can do this.
Okay, so wait, so what you're saying here, I think, is that this is that you're making use of the fact that you can find what this angle is, and you know that this is a right triangle? Does this matter?
Yes. This must be
So the claim here is, you want to find this distance, d. What do we know? We know this side. We know this angle, because it's got to be a right angle. Is that right? And from this and this, you're saying we also know that angle, right?
actually, you can know this because you know this two vectors. So you can do this cosine value of this
Okay.
directly.
Okay, but suppose let's say you know that angle. You know this angle. I'm just trying to, now you say you use the quadratic formula. You know this distance, you want this distance. Do you know this distance? You don't know that distance now.
I do not need to know because this x sine theta.
Ah, okay. That makes sense now. Okay, that's just trigonometry, right? And so now you're saying you would figure that out from that method.
Yeah.
Any other ways that you could figure that out? Okay, that's not how I would have done it if I had known everything I know about from my code so far. What would I have done? I last time showed you how to compute the closest point to a line, right? So the way I might have done it, and we'll decide which one we like better, I would find the perpendicular line, the intersection point between the perpendicular bisector of this, the perpendicular line that's perpendicular to this, that passes through this, right? And if I found the intersection point here, okay, that would be a way that I could compute then what the distance is. Do you agree? Okay. Any other ideas? Okay. So I claim we could find this distance. Now, is that once we know that distance, how do we then find out whether or not the rope intersects the pole?
There's another situation like this.
Okay.
In this way, I use. So there must be in these two status there must be one of them is larger than 90 degree. In this situation,
Okay.
in this direction, this vector is from this point to this point. This vector is from this point to this point. In this way, there must be an angle larger than 90 degree. And it's a condition that the one point of the group will never in the cycle, in the circle. So this situation will never happen. Like this situation will never happen.
Okay.
So there must be that. Yeah. If the any of the situations it must be offline.
Okay, so you're saying that I see. If both I see. What you're telling me is if you found the angles, either if both of the angle points lie on this side of well, wait a second.
If it's supposed on this right side, then there will be an angle larger than 90 degrees. You can see that when you see both sides, then the two sides, but then the two angles will both smaller.
Wait, why can't, for example, just to double check that thing?
This line is so this will also this is smaller than that.
Okay. So let's think this through and see if we understand this now. How do we tell whether or not what the real question is does the segment intersect the circle? That's really what the interesting question is. And there are two ways that we could do this. One is, in general, how can you tell if a line segment intersects a circle? The other he's noticing is that there is a promise that there is no, it is not that the point is in there. Okay? That's what he's saying, right? So this case is not going to happen. And so it sounds like what you did is you're saying you rotated the circle in some sense, conceptually. So so the circle was, so that the line was horizontal, basically. Is that right?
Yeah.
And the claim here is that if you now compute the angles, unless the angles to both points are on different sides of that, of this line, then it doesn't intersect. Is that basically what you're saying?
The same concept. My computation is a little more easier.
Okay, I believe that. Okay, any questions here? How would you tell whether it intersects it in general? Okay. Let's say we didn't have this consideration. Let's say it was possible for one point to be inside the pole. How would you tell whether or not a line segment intersects the circle?
We can first check if the point inside the circle.
One possibility is to check for that special case, right? Because in this case, the distance from the center to one of the points is going to be less than the radius. Everybody agree with that? So that would be one way that we could do it. Okay? Anything else? Okay?
You can compute the shortest distance between the searchman and their mark, and compare it with the radius of the search.
So what you're saying here is you would also compute, given the center of the circle, you compute what is the shortest point given the line segment. You can compute the shortest point between the center and the line. Is that right? And now then there's a question of, is this...
No.
No.
The line segments. The line segments.
Right, okay, so on the line segment, the shortest distance to the line segment. But the question is ultimately going to be, the way I would do that is I'd find what is the shortest point to the line, and then look at the relative position on the line of my closest point and the two endpoints. Either it's going to be between them, or they're both going to be on one side. Does that make sense? And then you can slide through and see that. Any questions? Okay. That tells us this case. How now do we solve the more general case? Now we know that it's going to hit that the point. I tell you this is the case. You now have a pillar. How do you figure out where the pillar, how long the rope is going to be in this case? Any ideas?
To enter line
It seems to me that the key thing here is finding the tangent lines, right? That you're going to be given a circle. You're given two outside points. What you really want to know is that are the tangent lines of the points. And where does that tangent point intersect? Is that right? How do you compute that then? How do we compute it? It would seem like what we'd really like to know is this, what that point is. Is that right? The tangent point between the circle and that tangent line. Is that what we want to know? Any ideas? What is it that we want to know in order to compute it? I think if we knew what the tangent points were, then you're trying to tell me the length is going to be this, plus the circular arc. Is that right? So how do we compute what that tangent point is? What do you want to know then? So what would suffice is we don't. If you don't want to know okay. So if we knew the tangent points, then I claim we would be done. But you're saying that's not really what we need to know. We can get away with less, perhaps, right? We could get away knowing the distance from here to here and the angle. Is that right? So how do we find that out? Okay, so how do we do that? We have this distance. You're claiming that at the tangent that's going to be a right angle. Is that right? We know this distance. Correct? Because that's the distance from here to here. We know this distance because that's the radius, right? And from Pythagorean theorem, indeed, we can know that distance d1. Does everybody agree with that? And I think similarly, we can do the same thing from d2 here. Is that right? How do we find out what that angle is?
Vector.
What?
Use vector.
Use vector, okay?
Already knew this one. This two. So and this vector is already known. So we can compute this vector's direction. This vector's direction. And here, two vectors. We compute this and this is
Okay? How people follow that? Okay, I don't think in terms of the vectors very much. Okay, so I was lousy at linear algebra. Does anybody have another way to do it?
We can calculate the angle between the two lines of the radius and then minus the.
Wait, which way is this? Show me. Okay, so that's an interesting possibility. Okay, so what he's saying is that that we know the center because we have this angle and that we now know what this angle is, and we know what this angle is. We can figure out what this whole total angle is because it's from this center and these other two. And subtracting that out gives us the remaining angle. Does that make sense? Yes.
How do we get the first angle?
How do you get the first angle? Okay, let's think about that.
It's the vector.
What?
The two vectors
given do you use A10 to get the angle between the x-axis and the vector in C++?
Okay. So wait. So again, we're dealing with the vector thinking again. Let's go back and think. Okay. So what is our situation again? I'm trying to make sure I understand it now. Here we've got that one point. Here we've got our circle. Here we've got our tangent. Here we've got our center. And we're interested in what this angle is. Okay? So what was the, so I guess one way to think about it. Okay, so what is the right way to think about this? Okay? One thing that's certainly true is that because we have, at least conceptually, because we have this point, we know the line that goes through that point. Here we have the slope of the line and a point going through this thing. Certainly, at least conceptually, we've got the equations of those two lines. Does everybody agree with that? And somehow converting the slopes to angles would suffice to give us the angle, the difference between the two of them. That's what I think is happening implicitly in the vector notation. Okay? But how would we actually, what would be the way that you would do it? Please write the equation up here. Okay? What is the way that you would find that angle? Show me.
Use the function in the library to calculate the angle between these two vectors. For example, this vector is y slope. This is and the angle between them is
It's our tangent. Well, the arctan is going to come back with an angle, right? This much I know. It's coming back from the angle, given the ratio of x over y. Okay? So that makes sense. Okay? Now the question is, do you have to worry about quadrants? What is arctan 2?
You mean the range?
Yes. What is this function? Is it a C function?
Yes. A C function. Its range is between this is also between.
Okay. So the important question is, this looks like it will give you the quadrant as well. Okay? Because it's not doing the dividing. It's giving you each of the arguments, right?
Yes.
So it can essentially give you the quadrant.
Suppose it is I assign 10 to this value, and if it is possible to be negative, if 10 is smaller, let's say, then I let it pass too high.
Okay?
And then it is positive. And then 10 means how many angles it is needed for this vector locate to this vector.
Okay.
And if there are if 10 is at least high, because the angle between two vectors must at most high.
Right.
So it is larger than high means what we calculate is this vector, this angle, not this.
Okay.
So I need to add 2 times and then this is the angle between two vectors.
Okay? Okay, interesting. I think I sort of believe that, actually. Any questions about that? It shows that a lot of the complexity here is maintaining the quadrants right and adjusting for the positive negative angles, which is definitely true. Okay, so once we've done this, now that we know the angle, what is the length of that arc? What?
Radius.
Pi, right, the circumference is pi times r, right? And it's pi times r times the angle divided by whatever the full range of the angle is, right? Okay? Does that complete the solution? Or is there anything else we have to worry about? I see one other thing to worry about, which is that if you want the shortest rope, you've got to consider it both ways. Correct?
You only pick the upper part.
Yeah, because it is already smaller than the upper.
Wait, so how do you solve that problem? Wait, so you're saying that the top part is always smaller than the bottom? Why is that?
Because the angles between two vectors is smaller than pi, but the bottom part, the angle is between those two vectors are larger than pi.
And you can.
Okay? Go.
It's much simpler. Here. Technically speaking, this part is larger than this one. So it's still not longer than this one.
Oh, wait, no. I don't see why, for example. What if the info looked like this? Now, the top part, in principle, looks like that.
The tendon will, this, you can see that the tendon will always extend. Of course,
Okay, so that's interesting.
this is the equal line. So only consider the this part.
Okay?
This part, because this one is larger, so this part, this angle is larger than this angle. This is larger.
Okay? So I agree that the tangent parts are the same length, and it's a question of finding the smaller angle. Okay? And that then I think completes that. Any other questions or details about this one? Did you guys do this one? You remember how long your solution was? Or not really?
Maybe 40 lines.
40 lines or so, okay? We have to be careful on this one, okay? Any questions? But I think we've beaten that one down. Any other questions? Okay? I think I'm going to believe that there are several ways of doing it, some of which are simpler than others, but I think we now understand how to do that. What is the next problem? The next problem is the birthday cake problem. Has anybody looked at the birthday cake problem? They want to tell me what the birthday cake problem is. Okay? Someone. Yes.
There is a cake, a circle-shaped cake, and on this cake there are two end points.
Okay.
And we need to find a line across the origin, so that it divides the cake into two parts, and on each part there are end points.
So here's our cake. Here's the center of the cake. And there are a certain number, 2 end cherries. 1, 2, 3, let's say 4. And the goal here is to find a way to cut the cake so that you get an equal number of cherries and cake. Does everybody see that? You're going to cut it with one cut so that you get an equal amount of cake. You got to cut through the center. Does everybody agree with that? Now my question is there always a way to also divide the cherries equally. You say no, why not? Show me an example. The problem comes, that you're saying, is when you have one line which has all the cherries on it. Okay, 2 or more of the cherries. If all the cherries existed on the same line, there is no way to split them up. Does everybody agree with that? What? You're saying that if all the cherries lie on one side of the line, well, if the cherries look like this, I claim this, if this was your problem,
I think it's a lot.
there's certainly a way to divide it, right? Because we just have to divide the line 1, 2, 3, 4, 5, 6 cherries. You know, put it there. Oh, I see. Oh, okay. Oh, I see. Oh, wait. Oh, I see what you're saying. What you're saying is what I had before, because I had the cherries on both sides. That was not a problem. The problem is coming when all the cherries, or enough of the cherries, are lying on the same line on one side of the center. That's where we've got a problem, right? Here, everybody gets you know, basically, if we cut it like this, one guy gets all the cherries. If we cut it like this, nobody gets the cherries. Is that right? What in this rule do we do about ties? When does a cherry go on the line that goes through? Okay? What happens to the cherry? What does the problem say about that? It says you're not allowed to cut on a cherry? Okay. It says cherries are not allowed to lie on the cut line. Okay? So under this story, it's not always, if you have collinear cherries, you've got a problem potentially, right? But they tell us there is always a solution, right? Actually, if we have no 3 cherries that are collinear, is the problem always solvable? Let's think about this special case, because this special case is actually kind of interesting. Suppose I promise you that no 3 cherries are collinear. There is no line that you can draw through the cherries. Okay? Is there always a solution? Yeah?
If the cut on A and the answer A, B must be integer, so there may be no solution. Because
Okay,
maybe
there's another problem which we're dealing with, which will get messy here, which is that they're also enforcing integer arithmetic. Let's get to that a little bit later. Question I have for you now is, if the cherries are in not this degenerate thing where they can have multiple cherries on a line. Suppose I guarantee you no more than 2 cherries are on a line.
I think about kind of case, can we put the cherries in a circle so that there is no viewpoint line that we cannot cut the without touching the cherry. So the cherry.
So you want to say is, suppose let's say the cherries are all in a circle on this side. Is that what you're going to?
Around the center of the circle.
Well, if you have equally spaced cherries, I think equally spaced cherries can certainly be cut, right? You have a hexagon of cherries.
Can a cherry in the middle of the cake?
What?
Can a cherry in the middle of the cake?
And let's say there's another problem, I guess. Okay, if you have a cherry on the middle of the cake, that cherry you can't divide. Let's forget about that special case. Assuming we have cherries in what we would call general position, where there are no cherries, no cherry is not sitting on the center. The cherry is not, no 3 cherries are collinear. Is there always a way to cut up the cherries? Cut it out to give equal amounts of cherries. Does anyone argue one way or another?
The cherry must be even number.
Even number of cherries. Is there always a way to divide it up? Let me tell you why I think there is, okay? Suppose, let's say we have a world where there are more cherries. How many cherries are there now? There's, well, 1, 2, 3, 4, 5, 6, 7, 8. Okay? Suppose I draw this line. And I consider, let's say, a plane that is rotating around. Okay? How many cherries lie on this side of the cut? There are fewer than half the cherries. Does everybody agree with that? This side there's fewer than half. This side there's more than half. Does everybody agree with that? Now let's look at what happens as I turn this line. Okay? When will the number of cherries on this side of the line change? Whenever my line bumps into a cherry. Does everybody agree with that?
Bumps to a cherry and there's, on the outside there's no cherry. I mean, there's two cherries not crossing the...
You're saying that so long as there are no two cherries... Oh, I see what we're saying now. So long as we rotate it, the cherries change one by one. The cherry count changes one by one. Then eventually we'll go from less than half of the cherries to greater than half of the cherries. Does everybody see that? And if the cherry count changes by one, okay, each time, clearly in the process of going from less than half the cherries to more than half the cherries, okay, then we are going to be done. Does everybody agree with that? So really the condition we need for there to always be a solution is that there is never two cherries that are collinear with the center. Does that make sense? So there's no 3 points that are collinear where we count the cherries and the center. That's the condition that we need.
I think if two cross the center is not an issue. Sweeping did not change the because they are swapping to another one.
Okay, so long as when we rotate it, the cherry count changes by one each time, we are done. It's true. Does everybody agree with that? So it is likely that there is going to be a way to do this. They're guaranteeing there always is a way to do it. Now my question is, how do you find where is the line that cuts the cherries? Any ideas? How would you go about doing this? Yeah?
Use the similar method to this, but firstly we sort the cherries in the angle first. The angle between
okay.
Yeah.
So you're saying you compute the angle associated with each cherry, right?
Right.
And now what are we going to do?
And then we find out can we position into two parts. The cherries into two parts.
Ah, okay. So what you're saying is the only lines that are really going to matter to me are that I pick one, that these lines, that if we consider the cherry angles, maybe we'll go back on the big picture here. Here we had 4 cherries. They define 4 angles, right? Your claim is actually, why don't we consider it all the way down to sectors? generate these things to lines. Is that right? Now are they all lines or no? This thing is that right? Or am I missing something? Must be missing something. Right? Which one am I missing? This got extended. This got extended. This got extended. This got extended. How come I'm missing one? Which one am I missing?
30 degree from
This one?
Yeah.
These two. These two I have.
Okay. So you're saying that this is. Okay. Yeah. Okay. Let's say yes. Okay. Now what you're trying to tell me is that if I pick one line within each sector, I can test whether that divides the cherries equally. Is that right? And in fact, how many sectors do I need to try? If I have n lines going through the center, how many sectors do I make? I think I make 2n sectors, right? But I guess if I stop to think about it, if I make this a line, I only really need to do all the ones on the top, right? So you're telling me check one line in each sector. And if that divides the count properly, I'll be done. Does everybody agree with that? Are there any complications? What is the complication? There is one. I think I agree with you that this should work in real geometry. What is the complication?
The lines are equal.
The complication here that they give is that lines are integers. It tells us that the lines must be of the form ax plus by. That's not a problem. But a and b have to be integers in the range minus 500 to 500. Okay?
I think we'll just switch all the lines.
Okay? Let's think about that. Could we now try all lines? How many lines are there
1 million.
defined?
It's smaller than 1 million. It's not all 1 million.
Well, let's think about that. How many are there? You're telling me that there are 1 million. Is that basically right?
1 million and most. Because there's some lines of the same.
You're telling me that there's minus 500 to 500. So there's 1,000 possible values for x and 1,000 possible values for y. Your proposal is that I take up all million of them. Okay?
I've tried it, but calculating is
What?
I've tried, but calculating is
Okay. So let's think about it. If we tried all possible lines, okay, it sounds like we would get into trouble. Right? Well, let's think about it. Why is that? Is that a problem or not? Okay? First of all, when you say you tried all possible lines, what did you do with all possible lines? Did you generated each line and then tested which side of the points does each point lie on?
yes.
Okay?
And then test if it equally cut the thing.
So his algorithm is going to take 1,000 by 1,000, which is, basically n squared, 1,000 squared lines. And for each of them, he's going to spend how much time to test it?
100.
100, the number of cherries. Is that right? So there seem to be two possible optimizations that we could do. One is to not test all the lines. The other is to find a faster way to validate it. Okay? How might we do it?
We can reduce the line by half. Yes. From y we can have negative 500 to another 500. X we can have 0.
So what you're trying to say is you only want to consider lines of, because we have a similar phenomena here, Your claim is that we're double counting the number of lines. If we pick, because what you're claiming here is that for every point here, -1, 1, is that it? -1, 1, that would be the same line as 1 minus 1. Is that right? So one possibility is we could have the number of lines with an observation like that, right?
And if the A and B has
Well, let me divide it by 2. Okay?
if the A and B has common
Divisors.
we can ignore them.
Everybody see this as another possible improvement. What is the difference between -1 and 1 and -2, 2? These would generate the same slopes. Does everybody agree with that? So we only need to do it over the relatively prime pairs. Is that right? Or one representative of each pair. Is there an easy way we can enumerate through those faster than what we're doing now? So that will save something, right? Yeah.
I still understand why we can cut it half and half. 1 minus 1, 1 and 1 minus 1 is just the same.
Well, the important point here is that a line, okay, is a, the lines have to go through the center. Does everybody agree with that? Let's consider the line that passes through -1, 1, and the center 0, 0. That also passes through the point 1, -1, right? Wait, okay, wait, no, that's, wait. You're not specifying it by points. Let's think about it. Is what you were saying right here now. If we were defining it by the number of points, another way to think about it is there's two different ways to think about it. Right now they're saying in terms of coefficients ax plus by equals 0, right? Now, I guess I will admit that I was thinking of it in terms of one of the grid points going through it. Okay? So go back and explain to me how you save half of them.
Ax plus by equals 0 is equal to minus ax minus by.
I see. So you're trying to tell me, okay, this is the explanation. You're right. Ax plus by equals 0 is the same as minus ax minus by equals 0. Okay? So that means what you're saying is that we might as well always take the wait, okay, so it's funny, I'm now blocking out here. What then do we have to search for? Okay? To avoid this duplication. Okay? We agree that since this is true, the line 30x plus 30y is the same as the line minus 30x plus minus 30y. Does everybody agree with that? And for that reason, you only have to check one of them. Okay? And so how is it that you were going to narrow the search space?
Just from x get from 0 to 500 and the y-axis get from negative 500 to positive 500.
So this is not possible.
He's insisting that x be positive. He's saying without loss of generality, x can be positive. And then y can be any other one, right? So that I now believe. Do you believe that?
This only say 35%. This kid up 25%.
Well, instead of trying all possibilities, he's having one of the dimensions. So that means he's saving half of the search space. Right? Okay. Now let's think about the second observation though. Is there a way that we can search through only the relatively prime pairs efficiently? That's an interesting idea. Well, but now you're still doing something that is n squared. Is that right?
Yes.
Firstly, we short cherries by its slope.
Okay. So we've also got the cherries sorted by slope. Now what?
And then do the binary search to find the range.
Okay.
Actually, I think if we make the variation fast enough, the time thing will not useful.
Right. So if there's two possibilities, two different ideas on the table. One is if we in fact can get rid of this order of 100, okay, then that's going to be a big win, and that may dominate. In fact, it turns out that there's still always going to be a quadratic number of relatively prime pairs. So your thing is going to be quadratic even if you magically could search through just the relatively prime pairs. But I don't immediately see a way to generate just relatively prime pairs. Okay? Actually, there probably is a way to do it. Okay? But what you're saying is a bigger idea would be to try to work on this side. Is that right?
I just make you can evaluate if a slot is valid. So you can, because you can use the formula of the line to compute which slot the line is.
Okay. So what you're saying is the way that you want to save this thing is that you want to build a data structure that tells you, it computes this thing, the sector diagram, and basically tells you that between this angle and this angle, it's going to cut 3. Well, wait. Suppose we have a line that goes between here and here. How many does it cut? Where are my 4 points? Here, in fact, it cuts 2. So this would be a bisector, right? In between here, how many would it cut? There would be 3 on one side. This would cut 3. Does everybody see that? Here, if we turn it on this side, it will cut 2. Right? Certain sectors will cut the right amount. Certain sectors will cut the wrong amount. That's what you're saying, right? And so one possibility is to replace this by a binary search. Take the slope of your desired line. Is that right? And once you have the slope of the desired line, do a binary search and see, to give you the count. That's what you're suggesting. Is that sort of what you're suggesting?
Just the Boolean value will be sufficient.
What?
Just the Boolean value will be sufficient.
So instead of telling you, storing the count, storing whether it's good enough, right? Whether it's half of the points.
And this can solve the prime problem, because you need to check if the prime problem, if the prime net already searched. But in this way, of course, the prime net will have the same slope, and just the binary search can do that.
Okay, but the binary search idea, I can believe that this now reduces to from 100 to log 100. Is that right? Number of cherries is 100. Oh, it's a log of... Yeah, it's a log of the number of cherries, because the number of lines in this diagram are a function of the number of cherries.
The number of sections actually is log 200. Because there are 100 cherries and they have at most 200.
Okay, it was a log of 200. Fine. Okay? So if you do it this way, okay, first of all, does everybody see how we can replace the explicit count by a binary search into a table of sectors? Every point, every AJ pair you define is going to have a slope, right? You want to find what sector is the slope of the line that you're interested in. If it is not in a sector, if it's in a sector that's not 2, that's not a solution. If it's a selector where it in fact does have half the cherries, then you win. So I claim you can reduce this to a binary search like that. But even that doesn't make me very happy. Is log of 200 much different than 100? Probably not very. Okay? So any other ideas how we can speed it up? Okay, you had an idea, right? No? Any other ideas how we can speed it up? Yes?
If you want to do the relatively prime pairs, they pre-calculate them all, and then reuse it for each testing.
So one possibility is that you say you can compute the relatively number of relatively prime pairs. So you would like to know, actually, for a given integer, A, you want to know what integers B are relatively prime to it. That's really what you want to know, right? So that if and then those would be corresponding with the interesting points. It's possible you could pre-compute this thing, which would be an n-squared computation. You're saying and use it for all test instances. Maybe that's an idea. Although I get worried about n-squared space. Is n-squared space a problem here? No? You have a million root per million integers?
We don't have to calculate from 0 to 500, right? This is only integers from negative 500 to 500.
No, but it's relative. What's relatively prime to each pair? So for A is what's relatively prime to 1, relatively prime to 2, relatively prime to 3. Does everybody see that? I do believe you could pre-compute that. Okay? But I do believe that if you store it, it's relatively large. And I do know that it's quadratic. If I'm remembering my number theory, there's a function. Anyone ever had a course in number theory? There's something called Euler's-Toshin's function, which is the number of relatively prime integers less than n. Okay? Is that right? And if I remember correct, the sum as I goes from 1 to n of the Euler's-Toshin function is something like n squared over pi, or I don't remember what it was, but it's quadratic. Okay? So with this idea, you will save something, perhaps. But you're paying quadratic space for it. Okay? And I don't think it's going to be a win ultimately. Okay?
I think if we build about the validation,
Yeah.
if we build a report and, for example, we accurate about 3 digits after the angle,
Yeah.
and build a report, you can look up in a constant time.
Why? What do? You can do hashing, or?
Just build a report, like hashing. I think if we
Oh, what you're now going to say is to avoid this quadratic, this binary search, you're going to build a quantized array of, for all angles from 0 to 2 pi, you divide the space of 0 to 2 pi into 100 or 1,000 quadrants, equal size, right? Or 10,000. And you're now going to describe which ones of these are true and which of these are false for that. And then now you can look up in constant time for a given slope. You round your slope to the nearest value, right?
Yes.
And then you look it up. That might work, although it still seems pretty complicated to me.
If you can just build a array, but I'm not sure it's accurate enough.
Okay, any other ideas how we might do this? Okay? See, I think that we're not quite using it, this data structure in the right way. It would seem to me the key issue here is that you know for any given angle range, what angle ranges are there? You know what angle ranges there are, that if there was an integer line between them, okay, it would suffice, right? Is the problem now, if I gave you this angle, and I gave you that angle, is there an integer with slope less than that? Can that be computed without exhaustively searching all the points? Does this make any sense what I just said? Okay? This seems to me to be quite reasonable. I don't have to search all the points. I only have to search the points whose angles, basically that are within these quadrants. Is that right? And I may not even have to search them. I know what I am asking is there a slope, okay, between these two, okay, that falls into this range? Isn't that right? How might I search for that more efficiently? Is there a way of doing that?
There is a way to generate all the fraction where x is applied to y.
Right. Right.
By
Okay, right. By adding the tops and adding the numerators and adding the denominators.
and we can generate this one in a very fast way. Usually, log n.
Okay? So what is he saying? I don't know if anybody has seen this before. There's this notion of this weird way that if I describe what it is, you should immediately say this can't work because it doesn't make sense. Okay? Suppose you want to find a fraction between 0 and 1. They're saying add the numerators and add the denominators and make the ratio there. You want to find a fraction between 0 and 1/2, add the numerators 1, add the denominators, 1/3 is going to be there. You want to find a fraction between 1/3 and 1/2, add the numerators and add the denominators. That's 2/5. Okay? When you did that kind of math in grade school, you would have gotten in trouble. Okay? Because it's exactly what kind of adding fractions that is. Right? But it does in fact generate all the fractions. Okay? That's an interesting trivia. Okay? But I'm not sure even that is necessary. Given this is your constraint, you want to know, is there an x and a y between R1 and R2? Right? That's what we're given. Is there, is there an x, right, all right, C1 and C2. Is there an x and a y between such that x over y is bigger than this and less than this, where x and y are between 500, minus 500 and 500.
There's a way to solve it.
What?
There's a way to solve it.
Solve it.
Like the closest integers C1.
Yeah?
And you can mix the smaller components. If C1 and C2 are smaller than 500,
What?
of course this is obviously so more 500. If it's larger than 500,
Okay.
and then if C1 is smaller than 500, then C2 is larger than 500.
Okay.
Will just be possible.
Okay, so you're suggesting not even really having to do any search of points now.
And if the two are both smaller, if they have the same integer tops,
Yeah.
and you divide x through, you can just divide x by this 500. It's the one.
Yeah.
So you can get 2 divided by 500.
Okay. We're running out of time, but
Okay.
let's say that what we agree somehow is, if you think about it this way, you should not have to try all pairs of points. Does everybody agree with that? That it's really reducing to looking for a point in a sector, and that there should be very few sectors that are necessary. Okay, that's the idea here. Okay? Any questions? Okay, I want to talk about the last problem. This is interesting. I think actually that was an interesting discussion. How big is it? Has anybody looked at the how big is it problem? Has anybody looked at the how big it is problem? Okay? Tell me about it. What is it?
If you the 8 circles radius find the smallest point.
Right, so you want to pack circles. You have a bunch of circles where you want to pack them so they're all rest on the bottom of the box. You want to find a way to pack the circles in so that the box is as narrow as possible. The height of the box, I guess, is figured by is forced by the height of the biggest circle, right? But then, what is the narrowest box that will contain all those circles? Okay? Any questions about that? How do we go about doing it? Any ideas?
Try all the possible orders of the.
Okay, so the first question is, suppose I give you the order of the circles. Can you figure out how narrow the boxes are? Right? How would you go about doing that? Okay? I give you the circles, the order of these circles. How can I find the tightest packing of these circles? How wide is their shadow? Okay? Use Pythagoras theorem. What does that mean? Okay? You want to claim if I have these two circles here. I guess I have to sit on the bottom of the box. Fortunately, it's a box like that, right? What is the idea here? Pythagoras theorem is going to tell me what? The distance between these two, given what? You've got the height of this one, you've got the height of that one, right? So that's the two things. Can you find out, you know, that the distance from here to here, I guess, fixes that, right? The difference between the two heights fixes this. And by Pythagoras, you now know what that one is. Is that right? So is that all that it's going to take? How do we find what the radius of the box is? What the boxes are? It sounds like if I give you the order of the boxes, the circles, you want to claim that I can just basically use Pythagoras theorem to find the distance between successive centers. Is that right? Okay? And then count the outsides. Is that all that's going to take? No, why not?
The circle may be too small, smaller than other, and you just simply slip under.
Oh, this is a problem now. What happens if I give you the big circle? I have a big circle and I have a lot of little circles. The size of the box is going to be this. Does everybody see that? So how do I solve this problem? How can I tell when the box is, when everything is somehow shadowed by another one? What? Check all the cases. Okay? I think yeah.
If you put into it and the total length is smaller or equal than the largest length, if you put into it then the length of the C2 is equal.
Okay, so the question that you're really saying, the case where this becomes a problem is when the sum of these lengths is less than the radius. That's when that case is going to happen. Okay?
There's another case, it's two.
Oh, but there's another case. What's the other
Two
case?
cycles is too large and they're smaller between.
What if we have a big circle, a tiny baby circle, and a pomelo-sized circle, a orange-sized circle, and a grape-sized circle, right? Now here you've got this problem, that in fact, you're right, this circle doesn't matter really whether it exists at all. So how do we handle this case?
This first one, third one, displacing.
Okay? So how do we deal with this one? That's actually kind of interesting. Okay?
The first one and second one distance past second one, third one distance smaller than first one, third one.
In this case, you're saying, which is it? The first one, second one, third one distance by itself is longer than what is in between it, right?
Well, if we assume there is a circle between them and then calculate the radius of that circle and compare the inversion circle with the circle.
Okay? There is some case analysis or something that has to be done here. Okay? Is there any other possible way around the problem? One possibility is maybe the optimal ordering. Right now you're proposing to compute for any circle what is the best ordering. I'm wondering if there's another way to do it, which is if there was some kind of a rule or something to decide what the best ordering was. Maybe you sort the circles by size, okay? Or something like that. That might make it easier. But that also might make it wrong without an existence proof, correctness proof. Any questions? So this is the most interesting of the ones. I think the problems today have been pretty interesting. Any questions? How many people got this one before, from the people who've done all the problems before? Did you get these before? You got this one before? Yes, okay? So it could be done. But think about it. Let's talk about it next time, okay? Any questions? So work on these, and next class we'll be dealing with the grids one. Okay? Thanks for your attention. Talk to you then.
Yeah, I want to ask why we need to search the cake. I don't know.
Okay. What do you
I just want to ask because I don't know why we need to search the cake. Because
Firstly, we sorted the cherries by the angle.
Yeah.
And then cut the cake by a little delta from it. And then
What's the little delta?
the little delta is limited to 0, but it's smaller than this one a little bit. Just a
Okay, so what we agree is, conceptually I'm agreeing with you.
Yeah.
Okay? So we kind of agree that when you're saying we want to go just an epsilon more angle more. An epsilon, but the question is, if that epsilon is going to be so large that it knocks you past your... so what I'm saying is only certain epsilons can be realized.
Yeah, so I just use this
Recognize
one.
the epsilon, epsilon finer than 1/500 can't be realized.
Yeah, but I don't think we need to search because the radius is only 100.
Yeah.
But the space we can use is 500. 500 and 500.
Ah.
Yeah, so when we enlarge this point, for example, we find this point is the double, it's not an integer, but we can enlarge to here.
Yeah.
You may be,
Yeah, so
you may cannot.
we can just use the absolute value or the other piece, just search around here. The four
So what
points.
you're going to try to do, you're saying is, you're going to say that out on 500, there are integers out on the side of the box. Right? There's like a box out, the furthest box. You're saying you might as well find out where does the real line sit, and then go to the next value.
Yeah.
And the claim is that that's going to have to be in the region, unless this region is so narrow that it can't be done.
Yeah, because here is the maximum is 10, 100, and here is 199 maybe something like that, because the radius is only 100. So I think it's large enough to have a cut on these 2 points. In the worst case, for example, here is 2 turns.
Okay, you have to do the precision thing, but that might be, it sounds plausible to me.
It's not
Okay.
because it's just what I want
Let's
to
do a
see.
precision calculation here. Yeah.
It's just what I want to see before. The precision is just the x over this. They want more than x. The difference between this and the C1 one is the fraction part is smaller than this one is not the final one. It is larger than
So I agree with you that this or this is a better way to do it than to worry about searching points. Okay, the searching points in the red. Okay.